Okay, welcome to Mechanical Engineering Systems. In today's class, we are going to talk about some advanced concepts that we started in last class. First and foremost, in the last class, we talked about this important equation. M divided by I is equal to sigma divided by Y is equal to E divided by R, where M is the moment, I is the moment of inertia, sigma is the normal stress, Y is the distance from the neutral axis, E is the Young's modulus, and R is the radius of curvature. Now this is called as the fundamental equation of bending. So fundamental equation of bending. Now, I want you to understand, think about a rod. So we have this rod that is attached to a support, and this is sort of fixed. There are three axes. So I'm going to call this Z axis, and then I'm going to have a Y axis, and I'm going to have X axis. Now imagine if my loading or if my force is about X or Y axis. If my load is about X or Y axis, please note that this is going to cause bending, which means this cantilevered beam will bend either about YY axis or about XX axis. If you want to find out the stresses because of this bending moment, you would use the fundamental equation of bending. Now, what I want to do is, I want you for a minute to understand what happens if we apply a torque, which is something like this. What would happen if we apply torque about the central shaft, the central axis? Then this rod is going to twist. So this rod is going to twist. And in that case, this there will be torque. So T is equal to torque. Now torque is also called as twisting moment. And the unit is Newton meter. And if you look at the equation, the fundamental equation of torsion, it is T divided by J is equal to tau divided by R is equal to G theta divided by L. This equation in principle looks similar to the fundamental equation of bending. But now try to understand, twisting moment is about the center line. It's about the axis that is passing through this rod. Please understand, whenever you have a circular section that is subjected to torsion, it is called as the shaft. And whenever you have a circular section that is subjected to bending, it is called as the bar or rod. So torsion is for shafts. Now T is the torque, J is the polar moment of inertia, polar moment of inertia. The polar moment of inertia structure, the equation is IZZ is equal to IXX plus IYY. For an example, if you have a circular cross section, for the circular cross section, IXX is equal to IYY is equal to pi d raised to 4 by 64, and IZZ is equal to IXX plus IYY, and that's going to give you pi d raised to 4 by 32. If you have a hollow cross section, which means you have a rod, actually you have a shaft with outside diameter DO and inside diameter DI, J is equal to pi d outside to the power 4 divided by 32 minus d inside to the power 4 by 32. Now, many a times, if you look at the power transmission systems, instead of solid circular shaft, they use hollow shaft. And the reason for hollow shafts is basically advantage in weight. For the same power transmission capacity, hollow shafts are lighter. There is another equation that plays an important role, which is the equation for power transmission. P is equal to 2 pi nt divided by 60, where P is power in watts, T is the torque, N is the RPM. So N divided by 60 is going to give you RPS. Alternatively, the power transmission P is given as product of torque. This is torque. And then this is angular velocity. Now, at this point, I want to give you a very important example on changing the characteristics of power. So this is very important. So if you think about power, power is energy divided by time. Energy is ability to do work. Energy can neither be created nor be destroyed. It only transitions or it only changes form. So in other words, the power is conserved and there will be some loss because of some friction or some other effects, some dissipative effects that usually gets converted to heat essentially and becomes entropy. Now, what I want to tell you before I go any further, let me ask you this concept of entropy. Does everyone know what entropy is? Can someone, I'm sure you studied thermodynamics either from Professor Rajdas or Professor Michelides. So I'm sure you must be very fundamentally strong. But just for my own understanding, can someone tell me what is entropy? Go ahead.
It's the amount of disorder.
Okay. What do you mean by amount of disorder? Okay, so I'll give you a very simple example. Imagine if you have a glass of boiling water. Okay, so that glass of boiling water, the water is hot, it's boiling, it has some energy. Do you agree with me? As soon as you pour that hot boiling water into a lake, the lake temperature does not increase. In other words, you had some energy, but as soon as you, so to speak, pour the energy into a reservoir absorbed all that energy, and that energy is lost. Please understand, energy can neither be created nor be destroyed. So basically, that heat energy got converted into form. That form we cannot use, or that form we cannot see, or the form that we cannot get the energy back. That it's called as entropy. Now, what does that mean? Is if you were to argue with your friends, family, or parents, that increases entropy. So don't argue. So please understand, entropy is the disorder. In other words, it is the form of the energy that is wasted. So that's why you don't want to get involved in any types of activities that increase entropy. Same thing happens in a mechanical power transmission system. Power transmission, even though we want it to be 100%, it will never be 100%, because there will be some friction, there will be some impurities, some lack of lubrication. So what it means is teeny tiny amount of power will be lost. So in other words, you cannot convert 100% of power to some other form of, say, electrical power to mechanical power. 100% conversion is not possible. Internal combustion engine, chemical energy or chemical power to the mechanical power, 100% conversion is not possible. So there is always some loss, and that loss is actually manifested or seen as heat. In other words, you would see rise in the temperature, and that temperature actually gets, the heat gets dissipated to the atmosphere. So think about it, the energy that gets dissipated to atmosphere gets converted into entropy. So entropy is always present, and as engineers we should try to minimize it. But please understand, as per the, the, the second law of thermodynamics, 100% efficiency is not possible. Remember, perpetual motion machine of second type. You cannot have all the heat getting converted into work. You will have heat coming in. You will have to have some heat rejected, and the difference between the heat coming in and heat that is rejected, that difference gets converted to work. Depending upon the means that you use for this conversion, one simple example is, if you were to use internal combustion engine, what is the fundamental concept behind internal combustion engine? You have chemical energy. What you do is you burn that fuel. Fuel has some calorific value. In other words, the fuel releases that energy, and with piston cylinder assembly, or if you have a rotary engine like a Wankel engine or a turbine, you convert that into rotary motion of the shaft. So you convert that into mechanical work. Now, think about it, like when we try to convert heat to work, we lose a lot of energy. And the reason for this is, I'm sure that you studied in thermodynamics that there are grades of energy. I give you a very simple example. If you rub your palms against each other, you are doing work, but you will see that your palms warm up. Your palms warm up. So work can easily be converted to heat. But now if you heat your palm, they will not generate work. In other words, you have work is the high grade of energy and heat is the low grade of energy. Converting from low grade of energy to high grade of energy incurs significant amount of losses. Everyone understood this? Now, next question is, what happens? Why the internal combustion engine has efficiencies of 30 to 40%? Because you are converting heat into work, and that also is not a direct transfer. You have the chemical energy. That chemical energy gets released, so there is some combustion losses, then there is some mechanical losses, then there are some overall losses, and then whatever is left is very teeny tiny amount of the energy that you started with. On the other hand, if you look at the electric vehicles, you will see the electric motors are quite efficient. In other words, if you think about the conversion of electrical energy to mechanical work generates less amount of entropy, and that's why it is more efficient. So if you look at the different types of energies, there are different types of grades of energies. It's always easier to convert from the higher grade of energy to lower grade of energy, but it is difficult, or you will incur a lot of losses if you go from lower grade of energy to higher grade of energy. Same thing happens in power transmission. So let me give you a very simple example. Power transmission, P is given as T times omega. T is the torque, omega is the speed. How many of you have driven a stick shift vehicle? Right. So have you noticed that if you want to start a stick shift vehicle, you need to put the vehicle in a neutral gear. So what happens when the vehicle is in neutral gear? So I will show you a schematic diagram, and we'll talk about this in a lot more detail later. So you have, say, internal combustion engine. IC engine means internal combustion engine. Then what you have is you have a shaft. Then what you have is you have a clutch, and we are going to look at the design of clutch. And there is something called as the clutch plate. And what you have here is you have the power transmission gearbox. So this is the gearbox. And then you have an axle. And this is your car. So this is the tire. So this is the gearbox. This is the tire. So when you start the engine, you cannot start the engine when the engine shaft is attached via clutch to the tires. You cannot start engine on load. What you need to do is, if you want to start the engine, you decouple the load from the engine and start the engine. When the engine starts, then what you do is you basically engage the clutch. Think about clutch. Those are like two plates. And basically those two plates come in contact. The plate on the driver's side is rotating. Plate on the driven side is pushed against the driver's side plate. And then because of the friction, the power gets transmitted. So that is the very simple fundamental understanding of friction clutch. And then from the internal combustion engine side, you get power to the tire. But that's how it starts. Initially, the vehicle is in neutral, which means there is no load. You start the engine, the vehicle starts. When the vehicle starts, you don't directly put the vehicle in the fourth gear. You put the vehicle first in the first gear. Do you agree with me? What happens in the first gear? In the first gear, I'm going to show it to you like this. You have speed omega 1. The speed is small. So basically because of the gear ratio, the speed is small. In other words, torque is high. and then that high torque allows that vehicle to catch up speed. The vehicle starts moving. After some time, you put the vehicle in the second gear. In the second gear, the speed goes up, torque goes down, which means the vehicle speeds up. Please note, power is going to remain the same. Only thing is you are going to manipulate either the speed going up, torque going down, speed going down, torque going up. So you have T1 omega 1. In the second gear, what you will do is the speed would further go up, which means the vehicle would speed up and torque would further go down. As you go in the third gear, as you go in the fourth gear, same thing is going to happen. As you go in the higher gears, vehicle speeds up, but the torque reduces. All of a sudden, if you have to go uphill, then the traction that you need at the tire is more, because it needs more force to carry the weight uphill. So at that time, you go to the lower gear, that way you downshift, and then basically what you do is the speed drops down, torque increases, and you have the torque to go up the hill. Everyone understood this? So this changes in the power transmission, changing the characteristics of torque and speed is achieved by means of gears. And we are going to talk about the gears, but the idea here is the gear design is based on the principles of torque transmission. Everyone understood this? Now at this point, I just want to take one simple example of torque shaft design, and I would teach you how to design a very simple coupling. So let me show you what this is. So you have a shaft on the input side. You have the shaft on the input side. You have the shaft on the output side. You have the shaft on the output side. And what I want to do is, I want to attach these two shafts securely. Now at this point, you may ask me question, hey, why not to weld them together? Okay, why not just to join them together? Please understand, if you have think about it like a motor, and if you have a pump, it's not a good idea to weld the motor shaft to the pump shaft. Multiple reasons. Because when you perform welding, first of all, you are going to heat and basically change the material characteristics. The joint will not be strong. It may weaken the internal components of the pump or the motor. And secondly, the whole thing is going to run at very high speed. So think about a slight misalignment would eventually cause breakage, and then that would actually fail the entire system. Instead of that, what I'm going to do is I'm going to attach a sleeve. So think about it like, what I'm going to do is I'm going to attach a sleeve, and this sleeve is going to go something like this. And this is not new. Believe you me, you have seen this. Have you used the 3D printers in the Innovation Hub? Have you seen the 3D printers in the Innovation Hub? If you go and see the 3D printers, there is a stepper motor. At the end of the stepper motor, there is a lead screw. And the stepper motor and the lead screw, they are connected with the sleeve coupling. This is the basic type of coupling that is used in power transmission. But there is a difference. If you look at the stepper motor attached to the lead screw for the 3D printers, the power transmission requirements are not very high. So what you have is, you have a simple set screw. You will see that you will have a simple set screw here, and there is a screw here that goes through the outer sleeve and then attaches to the shaft, or there could be a cutout on the shaft that is called as the D shaft. So rather than circular shaft, there is a D. So that way you can actually attach it more securely. However, if the power transmission requirements are stringent, if the power transmission requirements are high, what you do is you use something called as a key. So how does a key and keyway look like? So what you do is, this is the shaft. This is the shaft. And here, what you have is, you have something as a keyway. You cut a keyway. In this keyway, what you have is, you have a key. So basically you have a key. And then what you have is, you have basically, this is the sleeve. On the other side, you have the other shaft. And this other shaft also has the key. Typically, these two keys are perpendicular to each other. And this is the hub. This is the circular hub. So this is the, say, input shaft. This is the output shaft. And you have this key. Everyone understood? There are different types of keys. So you could have a rectangular key. You could have a circular key. You could have a Woodruff key, which is sort of a semicircular key, or you could have a taper key. Depending upon different types of applications, you have different types of keys. Keys are, can think about it like mechanical fuses. So for some reason, if the power transmission requirement, all of a sudden the output shaft freezes, but the input shaft still rotates. In this entire assembly, you don't want input shaft to break. You don't want output shaft to break. The easiest thing, just like a fuse that you want to break, is the key. So what you do is, you design the key as, for some reason, if the power transmission is going to fail, it has to fail at the key. So that will be the protection against the overload. In that case, what you would do is, you just go there, you will disassemble this power transmission assembly, see what the issue is, fix the issue, replace the key, and you are good to go. However, if your shaft, either on the input side or on the output side, fails, then you may have to lead, it may take you to pump overhaul. You have to rebuild the engine, or you have to rebuild the pump. If you don't want to do that in your design, you use key as a fail-safe mechanism. Everyone understood this? Now, I don't know if you have seen this, but if you look at the couplings that are used in 3D printers, they are not like rigid sleeves. Have you noticed that? There are cutouts. So if you look at the sleeve coupling that is used on the stepper motor and the lead screw, it's not a rigid pipe, so to speak. There are cutouts. And what is the reason for this cutout? So you will see that there are some cutouts like this. There are cutouts like this. There are cutouts like this. What is the reason for this cutout? The reason for that cutout is because of this cutout, there is some amount of compliance, which means slight offset in the shaft, slight offset in the lead screw and the stepper motor, or slight angular misalignment between the stepper motor and the lead screw, or maybe slight amount of vibration that is compensated by the compliance in the coupling. So basically that if you take that coupling out, if you try to move it, you will notice there is a little bit of give. It's not a solid rigid coupling. There is a little bit of give. So that is the reason when you look at the design of couplings, depending upon the amount of uh, eccentricity, either it could be translational or it could be angular, or translational or angular offsets. These couplings are used, and they are used to make sure that slight misalignment does not cause major harm and still the machine is able to function. So if you design a coupling, it is purely based on the torsional considerations. So the equation for torsion that we have seen will be used to design shafts and will be used to design couplings. Now, how do we design the shafts, and how do we design the coupling, and how do we design the key? So what I'm going to do is I'm going to give you steps to design shaft, steps to design key, and steps to design the coupling, a simple sleeve coupling, and then we will work out a problem. Now let me start with this sort of a thought experiment. So we have this shaft. This is a shaft, and this is the key. So this is the key. Now let me start. We are going to have some type of torque over here. So this is the torque. You agree with me? Torque is force times the radius, which means if I were to look at the key, which is over here, and I'm going to show you a simple square cross-section key. If I were to show you the key, on this key, there is force times radius. So on this key, there is this force times the radius. So F times R is equal to torque. Now my question to you is, if you look at the dimensions of the key, this is the length of the key. This is the width of the key. And I'm going to call this is the thickness of the key. This is the thickness of the key. So I'll show you again. This is the key. I'm just showing you the key. This is the length of the key. This is the thickness of the key. And this is the width of the key. What ways this key could fail? If this key has to fail, how can this key fail? this key can fail in shear. So just to give you an idea, there is a shear failure of the key, and I'm going to show you how that key shear failure would occur, which means top of the key would stay in the coupling and the other part of key would stay in the shaft. Do you agree with me? So half of the key would stay in the coupling and the say top half of the key would stay in coupling and the bottom of half of the key would be in the shaft. Do you agree with me? This is the way the key would be sheared. So there is shear failure of key. Shear failure. So if I were to find out the cross-sectional area that is resisting the shear failure, do you agree with me that that area is going to be this guy? So tau is equal to F divided by L multiplied by T. Do you agree with me? That is the area that is resisting the shear. So this is how the shear failure would happen. Next thing I want you to understand that the key could crush between the coupling and the shaft. So think about it, like you have this key which is in between the coupling and the shaft, and then basically imagine the key is made up with chalk, okay, or graphite or some other soft material. You will realize instead of shearing it off, it would get crushed. Do you agree with me? Crushing is a normal stress. So key could fail in crushing. So there is crushing failure of key. And for crushing failure, now what are the areas? As you can see, for crushing failure, do you agree with me? It will be half of this area. Do you agree with me? Because typically half of the key would sit in the shaft, half of the key would sit in the coupling, and the way the power transmits is shaft is going to apply force on the key is going to apply force on the coupling. That coupling would start rotating. There would be another key attached to the coupling. The coupling would apply force onto the next other key, and that other key would apply force to the driven shaft. So if you look at the crushing failure is going to look like F divided by W by 2 times L is equal to sigma. Please understand, crushing failure is the normal stress because the force is perpendicular to area. Shear stress is of course shear, which is load, is parallel to area. So do you agree with me? The key has only 3 dimensions: width, height, and thickness. With these 2 equations, we should be able to find out those 3 dimensions. Do you agree with me? How do you design the shafts? You will design the shafts using the fundamental equation of torsion. You will design the shaft using the fundamental equation of torsion. Now the next question is, how would you design the sleeve? Can somebody, I want you to think about it. How would you design the sleeve? So we looked at the design of shaft using the fundamental equation of torsion. We looked at the design of key, and that design of key would utilize the concepts from normal stress and shear stress. How would you design the coupling or the sleeve? Any ideas? I just gave you the answer. So coupling is a hollow shaft. Do you agree with me? So you would design the coupling by means of hollow shaft design. Please understand, as soon as you design the shaft, the inner diameter of the coupling is designed. You cannot have a shaft diameter different than the coupling inner diameter. So outer diameter of the shaft will be the inner diameter of the coupling, and then to determine the outer diameter of the coupling, you would use the equation for hollow shaft. Everyone understood this? And don't worry, I'll give you the recipe for design step by step. This is step 1, step 2, step 3, and we'll walk through the problem. The next important dimension is, so first you will design the shafts. After you design the shaft, you would design the key. After designing the key, you would design the sleeve. The last dimension that we need to find for the sleeve is the length of the sleeve. How would you find the length of the sleeve? Right. So the way you would design the sleeve is, the length of the sleeve is, you're going to have one key on the input side, one key on the output side. You really do not want those keys to be hitting each other, so you would add some sort of clearance. Typically, those keys are hammered in. You don't just place those keys in. There are tolerances just to make sure that those keys, they are sort of interference fit. So basically, you hammer those in. So what you will have is, the length of the coupling will be 2 times the length of the key plus some clearance. Everyone understood this? Now that brings me to the important question. If I were to follow the procedure, and this is important, if I were to follow the procedure, did you do shaft design in mechanics of materials and engineering design? Okay. If you follow the procedure that you discussed in mechanics of material, or if you follow the procedure that you did in engineering design, what are we missing? As soon as you cut the key in the shaft, so key cutting is done through some sort of milling operation or some sort of broaching operation. You have the shaft, or you have the milling tool, and you basically you cut the keyway. As soon as you cut the keyway, please understand the shaft is weakened. Why is it weakened? Because please understand that key has to have those sharp corners. Otherwise, the key will not remain in place. That would give rise to stress concentration. Your initial shaft calculation was based on the assumption that it's a solid circular shaft. That's no longer true, because we have added a small hole. Of course, it's an open hole, but that actually weakened the shaft. So what do we do? When we are going to, so that's why basically the finite element analysis component of design is super important. So as an engineer, when we are doing back of the envelope calculations, we will find out the diameter of the shaft, and say we find out the diameter of the shaft is 100 millimeters. It's a big shaft. To compensate for key weakening, we would make that shaft bigger, say 1.2 times. So I'm going to say, to account for key weakening, instead of using 100 millimeter shaft, I would use 110 or 120 millimeter of shaft diameter. Why? Because I know as soon as I cut the keyway, the shaft is weakened. That is a very simple approach. So that would allow you to design, but to verify the design, here is what you do. You create a CAD model, you import that CAD model in the SolidWorks, apply the torques to those assemblies, and perform finite element analysis. You find out what are the maximum shear stresses at all these interferences. Because please understand, now the loading situation is complex. You have torque. The torque is giving rise to deflection. That is actually deflecting the key. Then that actually is torquing the coupling. In addition to that, you have these sharp corners that would give rise to stress concentration. We can't take care of all these conditions, but the software with numerical approximations, it can take care of all these calculations. So you perform some hand calculations, do the CAD modeling, and then use the finite element analysis to check if your design is safe. Everyone understood this? Any questions? No questions? Okay, so what I'm going to do is I'm going to give you a step-by-step recipe to design a simple coupling. So design of sleeve coupling. So typically, when you design the sleeve coupling, the power would be given. This power. Speed would be given. The material would be given. So typically the shaft would be made up with steel. Key would be made up with mild steel, and sleeve could be steel, or sometimes you can have a cast iron. So these are the different materials that would be given. And as soon as they give you the material, essentially they give you the design properties of the material. Say they give you the yield stress and shear stress for the material, the shaft material, the key material, and the sleeve material. Step one, you have to use the equation P is equal to 2 pi nt divided by 60. From here, we have to find out the value of torque. Then we have to use the fundamental equation of torsion. So shaft design, step one, shaft design. We have to use T divided by J is equal to tau divided by R. And from here, we have to find out R, which is shaft diameter, shaft radius. Or we have to find out D, which is shaft diameter. Then we have to oversize the shaft to account for key weakness, to account for key weakening. D actual is equal to 1.1 to 1.2 times D shaft. Step two, is we have to find out design of key design. There are two types of keys. One is a rectangular key, Another one is square key. So in the rectangular key, the width and the thickness are of different diameter. So this is the length, this is the thickness, this is the width. Typically, if D is the diameter of the shaft, if D is the diameter of the shaft, if it's a square key, T is equal to W is equal to D by 4 for square key. And for rectangular key, T is equal to D by 6 and W is equal to D by 4 for rectangular key. And what you do is you find out the value of T, you find out the value of W, and then find length of the key using the equation sigma crushing is equal to F multiplied by W by 2 times L. The only unknown here is L, and then check key for shear. So tau is equal to F L times, so L times length of the key is, this is T, so T divided W L W. So, and you have to make sure that tau actual, so tau actual is less than equal to tau design. And the last step, step 3, design of sleeve. For design of sleeve, now one thing I want to tell you is sleeve, there are two ways to design. And please understand that sometimes the design process that I would discuss here may be slightly different than the process that is discussed in the textbook, because there are different ways to design the same thing. But at the end of the day, what we want to make sure that our design is safe. Our design performs the function that is intended. So the way you can design this, if you strictly want to use the mechanics of material equations, remember you are going to supply the same amount of torque. Same torque is going to go from input shaft to the coupling to the output shaft. So you can use the equation. Also, you know that this diameter is the diameter that you already found, which is D actual. So D actual. So this is the D actual. And what we want to find is we want to find out the D outside, which is D outside. So tau is equal to T divided by J multiplied by R. And this tau is the design strength. So this is tau design for sleeve. This is very important. sleeve could be made up with the same material as shaft, or sleeve could be made up with a different material. So depending upon what you choose, you have to use the appropriate value of design stress. And J is pi 32 d outside to the power 4 minus d actual to the power 4 multiplied by d outside divided by 2. Can you see that in this equation that I have written, tau is given to you. T we already know from step 1. The actual value is calculated. So the only unknown in this equation is D outside. Do you agree with me? Once this is done, you have to find out the length of the sleeve. You have to find out the length of the sleeve. And length of the sleeve is usually 2 times LS is length of the key plus some clearance. Now, some of you may ask me, how much of clearance? Now, at this point, what you should do is, you should open something called as mechanics handbook or design data book. That design data book, when you open the section on the key design, it will tell you the recommended values of clearances. But we are not going, so you can do that. Second thing, what you can do is, at this point, once you have gotten the inner diameter, once you have gotten the outer diameter, once you know the length of your key, you will go to a catalog. Like for example, you go to macmaster.com, or you would go to eBay, or you would go to Amazon, or you would go to Granger. So these are the vendors of mechanical components, and you will get the stock item. So these are called, you don't manufacture, because if you decide to manufacture it, it would be super expensive. What you will do is, once this is done, you will just go to maybe MacMaster car, or you would go to Granger, and then what you will do is, they have fantastic catalogs, and then you will go to the keys, select the keys, and then go select the couplings, and then just buy those. Everyone understood this? You don't make those. For example, if your key is say 4.7 millimeter, nobody is gonna give you key 4.7 millimeter. You just go for 5 millimeter. If your diameter comes at like 7.38 millimeter, nobody is gonna give you 7.3 millimeter diameter shaft. You go to 7.5 or you'll go to 8. You will round it off onto the higher side. But at the end, when you make these adjustments, you have to make sure that your overall design is safe. And how would you do that? This is how you do it. And believe you me, that as you go through this course, not now, your second or third assignment, I asked you to go to macmaster.com, select the component. They will give you CAD models for those catalog items. You download those CAD models, import them inside the SolidWorks or AutoCAD or Fusion 360 or whatever software you are using, Creo, and then actually create an assembly and perform a quick finite element analysis that will give you confidence in your design. You understood this? That is how you would start from the component level, go on to the assembly level, go to sub-assembly level, and go all the way to the big whole assembly of an engine or of a chassis or a car, something like that. That is how you would perform the design. Everyone understood this? Now, at this point, we have a choice. I can work out either an example to design the simple sleeve coupling, or I can slide I am at slide 4. Oh, yes, slide 4. Okay, okay, sorry. Yeah, of course. Okay, now as soon as you are done with actual, that is what you should do. So hold on a second. So, okay, you want to go to 4. So as soon as you are done with the shaft design, you will have to stick to actual. What do you want me to do? Do you want me to work out a problem, or do you want me to discuss the flange coupling? Okay. So let's design a sleeve coupling to transmit 1 kilowatt of power at 1000 RPM with overload factor of 1.2. Shaft and sleeve made up with alloy steel with crushing stress. Actually, you don't need crushing stress for this. By the time you are done with the course, you would get sort of a feel for the materials, their material properties, what properties you should use. So typically for the steel, the crushing stress can go anywhere between 150 to 200 Newton per millimeter square. Tensile stress can go from 70 to 100 Newton per millimeter square. And shear stress would typically go from 45 to 60 Newton per millimeter square, depending upon the grade of the steel. This is the alloy steel. This is the alloy steel. So I'm going to assume tau shaft is equal to 60 Newton per millimeter square. You can actually use mechanics handbook or material handbook to find out these values, or you can just Google tau. So the key is made up with mild steel. Tau key is equal to 45 Newton per millimeter square. Sigma C is equal to 100 Newton per millimeter square. One thing please understand, this gives you an overload factor. Step 1, P is equal to 2 pi NT divided by 60. Power is 1 kilowatts. 2 times pi times speed is 1000 times T divided by 60. From here, you're gonna get value of T. Now, what is its overload factor? Whenever you start a machine, the machine is at rest. So it has to overcome the inertia. It has to overcome the residual static friction. Kinetic friction is always less than the static friction. So initial power requirement could be higher than the steady state power requirement. Initial torque could be higher than the steady state torque. So whatever torque you get, you would say T actual is equal to 1.2 times T. Are you with me? Next thing is step 2, shaft design. When you design the shaft, you would use T actual tau divided by R. So will you substitute the value of T actual? J is pi by 32, and we are going to use solid shaft by 32. D by 2 is equal to shaft is 60. From here, you are gonna get value of D shaft. Are you with me? Then to compensate for key weakening, D shaft actual, you can use 1.1 times D shaft. Step 2, I'm gonna use the square key. For square key, T is equal to W is equal to D by 2. So T is equal to W is equal to D shaft actual divided by 4. Then to find the length of the key, sigma crushing is equal to F divided by T by 2 multiplied by L. F is equal to T actual divided by D shaft actual by 2. T by 2 is D shaft actual by 4 multiplied by 1/2 multiplied by L is equal to 120. The only unknown in this equation is L that can be found out. The next part is tau. Tau is equal to F divided by L multiplied by T. And here T and W is the same, that's why it doesn't matter. So that's why I'm just using T, but let me say W, T divided by W. F is T actual divided by D shaft actual divided by 2. L you know, W you know, and you have to make sure this is less than T design. And this is 40, how much is T design? 45. 45 Newton per millimeter square. Last step is step 3. So there are 2 ways to solve this. I'm gonna solve it of the first way, where tau is equal to T divided by J multiplied by R. The sleeve is made up with the same material as shaft. You know the value of torque, pi by 32. D outside to the power 4 minus D shaft actual to the power 4 multiplied by D outside divided by 2. The only unknown here is D outside, and you will get the entire design. Last step is the length. 2 times length of the key plus 5 millimeter clearance. So 2 times L plus 5 is the length of coupling. With this, we will stop, but I will leave this design process so that you will have some time to copy it down if you're interested. And I don't have a calculator. If you have a calculator, if you can quickly, in 1 minute, tell me the answer, I will be happy to write those answers. If not, that's okay as well. Yeah,
I could understand the different stresses, but in what cases would you use the rectangular versus the square key?
totally depends if you want to use. I have used mostly square keys, but sometimes if the design requires it to be a rectangular key, there is a consideration that you
Because
do.
most of the times you do this, the key is like sacrificial, right? If you over torque, it'll shear the key.
Yep.
Okay. So for the square.
Yep, that's what I have used.
Okay.
Just make sure you post these on Canvas.
No, I won't be able to because the Zoom crashes, so I won't be able to put the slides. But I have recorded the videos. I would be able
Okay.
to